Last year, the number of electric vehicles worldwide increased by approximately 33%, reaching 55.8 million fully electric and plug-in hybrid vehicles by the end of the year. But when winter arrives, a single question pops into everyone's mind. Why is my range disappearing? Most people believe the answer is simple. The battery gets cold. But in reality, the main culprit is something far less discussed: thermal inertia. Today, I'm going to explain why and how an electric vehicle's range can drop by nearly 50% in winter. And I'll also show you, using scientific principles, a 15-minute rule that can help preserve up to 30% of your range, even at -10 degrees Celsius. If you're ready, let's head down into the garage of thermodynamics. Anatomy of an EV thermal management system. The diagram on your screen shows the anatomy of a modern electric vehicle's thermal management system. On the left, we see a PTC heater, a positive temperature coefficient heater. It works just like an electric space heater. Electricity goes in, heat comes out through a ceramic matrix. Simple, immediate, and inefficient. On the right, we have a far more complex system, the heat pump. This setup includes a compressor, condenser, and sophisticated valve systems, similar to Tesla's octavalve architecture. The key metric used to compare these systems is COP, coefficient of performance. A PTC heater always has a COP of 1. That means 1 kilowatts of electrical energy produces 1 kilowatts of heat. A well-designed heat pump, however, can reach a COP of up to 5, meaning 1 kilowatts of electricity can transfer 5 kilowatts of heat. How temperature and time change efficiency. This chart shows which technology is more efficient depending on ambient temperature and driving duration. The horizontal axis represents time since the start of driving. The vertical axis represents outside air temperature. HP stands for heat pump. The percentages indicate relative efficiency compared to PTC heating infs. At 0 degrees Celsius and below, something interesting happens. During the first 5 to 10 minutes, heat pump efficiency drops dramatically, sometimes as low as 10%, even falling below PTC performance. Why? Thermal inertia. A heat pump doesn't just heat the cabin. First, it must warm up. Coolant fluid, metal pipes, heat exchangers, internal components. In cold conditions, the system must heat its own mass before delivering warmth to you. Have mild climate scenario, plus 15 degrees Celsius. At plus 15 degrees Celsius, the situation is crystal clear. The outside air contains plenty of usable thermal energy, making it easy for the refrigerant to extract heat. The battery also operates close to its ideal temperature range of 15 to 35 degrees Celsius, minimizing thermal management load. In this scenario, the heat pump surpasses PTC efficiency within the first 10 minutes. By 30 minutes, the efficiency advantage exceeds 350%. Here, the heat pump is the undisputed winner. The critical point, 0 degrees Celsius. At 0 degrees Celsius, pay close attention to the intersection point on the graph, right around 10 minutes. For the first 10 minutes, PTC heaters are more efficient. They deliver instant hot air. After that, heat pump efficiency rises rapidly. Performance climbs toward 200% efficiency. Vehicles without heat pumps, such as some configurations of the Togg T10X, remain locked in the inefficient zone, consuming energy at a 1-to-1 ratio. With a heat pump, meaningful energy savings begin once your drive exceeds 10 minutes. Klar, cold weather. At 10 degrees Celsius. At just 10 degrees Celsius, physics starts pushing back. The break-even point where the heat pump overtakes PTC shifts to around 15 minutes. The colder the air, the harder the compressor must work to extract usable heat. On short trips under 10 minutes, heat pumps can be inefficient. But after 15 minutes, and especially beyond 30 minutes, heat pumps can still provide up to 90% efficiency advantage, helping preserve driving range. Modern EVs improve this further by integrating waste heat from motors and batteries into the heating cycle. Extreme cold, 25 degrees Celsius. At 25 degrees Celsius, the graph flattens. The heat pump approaches its physical limits. Extracting heat from outside air becomes extremely difficult. Its top drops toward 1.0, similar to PTC heaters. At this point, hybrid heating strategies become essential. Examples include Mini Countryman, which uses PTC heating first and then transfers load to the heat pump. Tesla's loss mode, which sends current through motors and compressors without producing motion, turning them into controlled heat sources. The real enemy, thermal inertia. This is the core issue. On screen, the contrast is clear. PTC heaters deliver heat instantly. Heat pumps initially consume energy without delivering cabin heat, often called vampire consumption. Why? Because the battery pack and coolant system can have a thermal capacity of around 100,000 joules per Kelvin. That massive thermal mass must be heated before comfort heat reaches the cabin. This is why short winter trips, like a quick run to the grocery store, often show poor efficiency, even in heat pump-equipped vehicles. Waste heat recovery changes everything. After about 15 minutes of driving, motors and batteries begin producing usable heat. This is where WHR, waste heat recovery, comes into play. Instead of pulling heat from freezing air, the system harvests heat from electric motors, power electronics, battery packs. When combined with a heat pump, 1 kilowatts of electrical energy can deliver up to 4 kilowatts of cabin heat. This technology is one of the key reasons EVs can maintain range during long winter drives. Final takeaways. As outside temperatures drop, PTC heaters remain fast but inefficient. Heat pumps start slow but become far more efficient over time. Advances like silicon carbide inverters and improved insulation help, but physics still wins. Fast heating consumes energy. Efficient heating takes time. Your winter range is determined not just by battery size, but by the thermal inertia of the entire system surrounding it. 3 practical tips. Preheat while plugged in. Let the grid handle the vampire consumption, not your battery. Use seat and steering wheel heaters on short trips. Heating people is far more efficient than heating air. If you have a garage and a heat pump, preheat gently. Starting from a warmer environment significantly reduces energy demand. Thermal inertia goes far deeper than what we covered today, and there are many fascinating aspects still worth exploring. I'll dive into those in future videos. If there's a topic you're especially curious about, let me know in the comments. I genuinely enjoy deep technical research, whether it's electric vehicles or other advanced technologies. These videos take days of research to prepare. Your comments, likes, subscriptions, notifications, shares, and watch time are my only motivation. And a special thank you to my channel members for your continued support. Until next time.